Hello, in this video I'm going to explain about function analysis and graph. If you remember, the elements of a function that we're going to analyze this partial are the following: the restrictions and domain of the function, x and y intercepts, symmetry, vertical asymptotes and gaps or empty dots, horizontal or slant asymptotes, and then we're going to sketch the graph and find the range. For the first element, the domain, remember that depending on the type of function, the restrictions, that is, the set of values of x that cannot be taken, change. There are different types of functions that we're going to analyze, although for this first partial, we're only checking the second one, the rational function. The polynomial function. For the polynomial function, there are no restrictions. That means the domain will be all real numbers. For the rational function, the denominator has to be different than 0. So you need to do that and then find the value of x. For the radical with even power function, the radicand, that is the expression that is inside the square root, has to be greater than or equal to 0. Then for the exponential function, there are no restrictions, so that also means the domain will be all real numbers. And then for the logarithmic function, the argument has to be greater than 0. In this case, for example, I have this function, which is f of x equal to x squared plus x minus 2 over x squared minus 3x plus 2. To find the domain, first the restriction, the denominator has to be different than 0. So x squared minus 3x plus 2 has to be different than 0. We factorize that. How? Well, by looking for two numbers that multiply give you positive 2 and add that give you negative 3. So it will be x minus 2 times x minus 1 different than 0. And then we're going to separate the factors. Each one of them is going to be different than 0. We isolate x for both, so we have x different than 2 and x different than 1. So my domain is going to be that the x belongs to all the numbers except the elements 1 and 2. Those two are going to be my restrictions of the function. The second element are the x and y intercepts. Remember, the x-intercepts are intersection points between the function and the x-axis. And how do you find them? Well, you just need to let the entire function equal to 0 and then isolate the x. And for the y-intercepts, those are the intersection points between the function and the y-axis. And you find them by letting x equal to 0, just the x equal to 0, and substitute or evaluate f of 0. Example, it's the same function, but at the second step, for the x-intercept, if you observe, the y has to be equal to 0, so the entire function is equal to 0. In that case, remember that the whole denominator passes to the other side, so it becomes 0 times the denominator is 0. So you only have the numerator, x squared plus x minus 2 equal to 0. We also factorize that if it's possible. In this case, it's going to be x plus 2 times x minus 1 equal to 0. Therefore, each factor is going to be x plus 2 equal to 0, x minus 1 equal to 0. We isolate, so it's going to be x equal to negative 2, x equal to 1. The x-intercept then, as a point, has to be given as the value of x and the value of y is 0. So the point A, or call it whatever you want, it's going to be minus 2, 0. In the case of the 1, that's not an x-intercept, but why not? Because in this case, if you remember, in the restrictions, we found that 1 was an exception, a restriction. So that means that that value 1 is not an x-intercept. Be careful with that, please. Try to analyze always the domain first and then the values, and then check what happens. In the case of the y-intercept, we let x equal to 0. We put for every x equal to 0, we evaluate f of 0. So we evaluate, so at the end we have minus 2 over 2, and that's just equal to negative 1. So my point of the y-intercept will be point B, 0, minus 1, or negative 1. Let's continue. The symmetry. You remember the mathematical analysis of the symmetry says that you need to evaluate first f of negative x. If f of negative x is the same or equal to f of x, the function is symmetric to the y-axis, and it's called an even function. If the f of negative x is equal to the negative of f of x, the function is symmetric to the origin, and that's an odd function, and when neither of the previous two apply, the function has no symmetry. Also, remember that there's another way to do it, which is just giving values to that. So we just need to analyze f of a certain value x and f of the negative of that value. And we just need to check if it's equal to the original, or the same value was negative, or totally different. I'll give you an example. Here, same function. We're analyzing now with 3 and negative 3. Remember that the value that I'm checking has to be a value that exists in the domain, so the restrictions are off the charts. In this case, f of 3, when analyzing the function, we obtain 10 over 2, which is 5. And then f of the negative of that value, f of negative 3, we'll apply the same thing, we evaluate, so we have 4 over 20, which is 1/5. And they're totally different. If they're different, that is, not the same value, not the same sign, not anything, then we say that the f of x, the function, is not symmetric. The next element, vertical asymptotes and or gaps. Remember that gaps are also empty dots, the same way to express it. In this case, you need to use the restrictions. Once the restrictions are identified in the first step, we need to do an analysis of the limit of that restriction. In this explanation, the restriction is going to be x equal to a. In the example, I'm going to give you numbers. So we're going to evaluate limit as x approaches a, the full limit of the function that I have. We have two different possible answers. If the answer of that limit is a number over 0, then x equal to a is going to be a possible vertical asymptote, and you need to do something else, which I'll explain later. Or if the answer is 0 over 0, then a is a possible x-coordinate of a gap. If x equal to a is a possible vertical asymptote, that is the first option, then the second step is to analyze both the lateral limits as x approaches a, that is, x approaches a from the left, x approaches a from the right. You analyze that with the explanation that we did in class last week. So if at least one of those lateral limits go to positive infinity or negative infinity, at least one of those limits, then you may conclude that x equal to a is going to be a vertical asymptote, and that's it for that value. The other option is that a is a possible x-coordinate of a gap. In this case, for example, the second step, that is when you have 0 over 0, and you obtain 0 over 0, so the second step is going to be to analyze the original limit again, but this time you need to modify the function in order to simplify it. Remember, if the function is a simple rational, that is, with polynomials, you use algebraic procedures, that is, factor and simplify. If the function has radicals, that is, square roots, you need to rationalize it, which is multiply by conjugates and simplify. And the third option is that the function has fractions, complex fractions, then you simplify the fractions. After you simplify, you need to evaluate the limit again with the equivalent function. And then the gap has coordinates x, y, where x is the value that you're checking, and y is the answer to the limit. I'll give you an example. In this function, we have two restrictions. If you remember, the two restrictions were 1 and 2. So, to analyze the fourth step, vertical asymptotes are our empty dots. Check the restrictions. First, let's check at x equal to 1. We analyze the limit x approaches 1. We evaluate that, and we obtain 0 over 0. That means that x equal to 1 is possibly an empty dot. And then we need to factor the function, so we have x plus 2 times x minus 1, and x minus 2 times x minus 1 in the denominator. Simplify, evaluate again, so you have minus 3. So therefore, the empty dot or gap, you can change the letter, I just put g, will be 1, negative 3, and that's going to be an empty dot. For the other restriction, x equal to 2, then we have the limit of the function, x approaches 2. For the function, we evaluate, but now we obtain 4 over 0. That doesn't exist. That means that x equal to 2 is going to be possibly a vertical asymptote. So now this time you don't factorize, no. we need to analyze left and right lateral limits. My recommendation is that if for any reason you already simplify the function in a previous step, now use the simplified form, but if not, use the full function again. So from the left, from the right of the two, we evaluate, so between number 4 over 0 from the left, that is equal to negative infinity, and 4 over 0 from the right, which is infinity. At least one of them is infinity or negative infinity, so therefore x equal to 2 is a vertical asymptote. The next step, horizontal or slant asymptotes. We analyze both the end behavior limits, that is x approaches infinity, x approaches negative infinity, infinite limits. We check the answer. If the answer to those two limits, or at least one of them, is a number c, any number, then the horizontal asymptote is going to be y equal to c. If both answers are positive or negative infinity, or both don't exist, then there is no horizontal asymptote. Let's check an example. Same function, we check in limits at infinity and negative infinity. Limit of a function x approaches infinity. If you observe, and I'm checking the simplified form, you can also check the original one. So you evaluate, you have infinity over infinity. And then, if you want to, we can use the short procedure. If not, you can use the long one. At the end, the answer is going to be the same. If we use the short procedure, the degree of the numerator is 1, the degree of the denominator is also 1. We divide the leading coefficients, 1 divided by 1, and the answer is 1. Limit x approaches negative infinity, same situation, we evaluate, same degrees, same coefficients, the answer is also 1. Therefore, y equal to 1 is an horizontal asymptote, and there are no slant asymptotes. I'll explain how to know that. The only way for you to have a slant asymptote will be if there is no horizontal asymptote. I'll leave this for another video, but in the example that I gave you, since there was an horizontal asymptote, we can conclude that there is no slant. So it's either horizontal asymptote or slant. I'll explain this in another video. And then lastly, when you have everything to graph, you need to use the obtained elements. Plot the x and y intercepts, draw the horizontal, slant, and vertical asymptotes, plot the gaps or empty dots, sketch the graph, and then get the range. And if you want to, you can evaluate with more values of the function to graph more exactly. So in this particular example, according to my information, the horizontal asymptote was y equal to 1, vertical asymptote was x equal to 2, x-intercept at minus 2, 0, y-intercept at 0, minus 1, and the gap was at 1, minus 3. Therefore, this is going to be the graph, but also by checking the behavior before and after the asymptote. If you remember from the limits in here, before the 2 it was negative infinity, after the 2 it was infinity. So before the 2, negative infinity, after the 2 is infinity. And the range, remember the range are the values of the y, so it's all the numbers except what? The value of the empty dot or gap, which is negative 3, and the value of the asymptote, which is 1. Very good. I hope this helps for you to understand it better. It's also a summary. In a video that I'm going to do later, I'm going to show you also how to get slant asymptotes. Thank you very much for your attention. See you in class.